Hi, friends. Today on 1 Minute Math, we're looking at the full-length explanation of how to find a limit. This is for AP Calculus or your honors calculus class in high school, Calc 1 in college. You might also be experiencing calculating limits or computing limits if you're at the very end of an advanced AP or honors pre-calculus class. But when we talk about a limit, what we're talking about is a value that a function either achieves or approaches, even though it might not actually get there. Okay, so this word limit, sometimes we think of limit colloquially meaning like an upper bound, but in this broader concept in mathematics, this often happens in mathematics since mathematics is not an English-based language. I mean, we use English words, but many of the foundational concepts and the people who wrote about mathematics when all of these concepts were being discovered were not native speakers of the English language. So we get a lot of words that have a different colloquial meaning than the meaning that they have precisely in mathematics. Here in math, when we're talking about a limit, it doesn't have to be an upper bound. It doesn't have to be a lower bound. It doesn't have to be something that you don't actually achieve or that you can't go beyond. It's just a value that you approach. A limit is a value, a value that f of x, so we're talking about y values, f of x approaches and might achieve. So f of x might actually equal this value, but it at least approaches this value. All right, and the three basic ways that we're going to calculate a limit, assuming that we're given a function algebraically or given this limit expression algebraically. For example, if I asked you to evaluate the limit as x goes to 3 of 2x plus 5, okay? This is a very easy one, but this is what they look like, right? We're given the lim, that means we're going to be calculating a limit. X and the little arrow, x approaches that number, so that's the x value around which we're going to be looking, but never exactly at that x value. And then the expression that's in the parentheses there, that's the function that I'm going to be evaluating as x approaches 3. What do those values approach? Okay. And this one's actually pretty easy because I can plug it right in. Our first strategy is to substitute, right? I plug 3 in for x, and I see that this is a very normal expression. There's no weird quotients. There's nothing like a square root of a negative. There's nothing that I can't just evaluate. I have no reason to believe that this function 2x plus 5 has any kind of unusual behavior like discontinuities, asymptotes, holes, anything like that. And my answer is simply the answer I get there. 2 times 3 plus 5 equals 11. And I properly used equal signs between each of those things. A limit equals a number. So if you're given a limit expression, the next thing that you write that it equals should be a number or another limit expression, which will ultimately equal a number. Okay. So now let's say I'm asked to find the limit as x goes to 3 again, but now I'm going to be asked for the limit as x goes to 3 of x squared minus 9 over x minus 3. And this is bad. Okay, because now when I try to plug in 3, if we try substitution, that should always be the first thing that you try. But if I try substitution, 3 squared minus 9, I get 0 on the top. That's not terrible. 0 divided by a number would still equal 0. But I also get 0 in the denominator. And 0 over 0 is a very quintessentially weird expression. All right, as a brief diversion here, let's talk about the fact that 0 divided by a number, I'll take 8 because 8's my favorite number. 0 divided by a number is 0. If I have no things and I divide them among 8 friends, we all get no things. A number divided by 0 does not exist technically. It might approach an infinite number. Like if I had 8 divided by 0.1, I would get 80. 8 divided by 0.01 would be 800. As that value on the bottom gets smaller and smaller, my output gets larger and larger. So this thing might go to positive infinity, it might go to negative infinity, or it might just not exist, but it's weird. Right? When we have a number divided by 0, we have to do more work to determine which one of those things is going to be our answer. And if we have 0 over 0, we just scream and run. No, we don't. We're smart and we will figure it out. But 0 over 0 is an expression that, like, it can really equal anything. And we have to look at the specifics of what we were given to start with. What expressions were we evaluating? How did we say this one's going to approach 0, this one's going to approach 0, before we make a conclusion? But really, when you see 0 over 0, that means you're not done. Do more work. And for the love of all things holy, do not write equals 0 over 0. You might accidentally, like, burst into flames. Okay, that's a classic no-no. Even writing 0 over 0, I feel a little bit itchy here, writing 0 over 0 on my page. But you definitely don't write equals 0 over 0, and it doesn't equal 0, and it doesn't equal infinity. We don't know yet. All right. In this case, when you get a 0 over a 0, algebraically or numerically, the best thing that you can do here is try and factor. My algebra instincts are telling me that I should factor that puppy on the top. And let's see what happens. I get x minus 3 times x plus 3. Well, would you look at that? I usually can't cancel out expressions like that. You can't cancel out algebraic factors because if x equals 3, this whole thing goes wonky, and I can't just make it go away. But isn't it awesome that since we're looking at the limit as x goes to 3, we're deliberately saying we're not looking at x equals 3. We're looking at x equals 3.1, 3.001, 3.001, 2.99999. We're looking right around x equals 3, but not exactly at it. And that is why I can cross out those x minus 3s. That means that I'm now looking at the limit as x goes to 3 of x plus 3, and that's pretty easy. At this point, we can just plug in our 3 for that x, and we get equals 3 plus 3, which is 6. Bam. Now, the last thing that could happen is that maybe we're given an expression that can't be simplified. If I asked you to find the limit as x goes to 0 of sine x over x, I can't plug in. If I plug in, I get 0 on the top and 0 on the bottom. 0 over 0 is quintessentially bad, so I can't do that. There's no algebraic simplification because sine x is not an algebraic function. This is a transcendental function. So I can't factor anything out. I can't cancel anything, and I need to do something else. And that's where we're going to use graphs or tables of values to approximate. And let's check out a few examples of all of these things. I'm just going to point out here, if you are watching this video and you're at the end of your calculus class, maybe you're reviewing, there are a couple other things that you might want to do as well, which would be to recognize the limit definition of the derivative, or maybe apply L'Hopital's rule. Those are things that, ways that you can evaluate a limit once you have mastered pretty much the whole of derivative calculus. Once you understand derivatives and applications of derivatives, you could approach limit problems using those two strategies very nicely and very efficiently. But we're not going to do that now because this is kind of an intro thing. Look for my L'Hopital video if you're in that situation and you want to see how you could use the limit definition of the derivative or L'Hopital's rule. All right. So here we go. Let's take these 3 examples, and actually this one down here, I want to just do limit as x goes to 0 of sine x over x. Beginning at the beginning, I'm going to first try plugging in 3 times 0.5 squared times 2 times 0.5 minus 1. That would be 3/4 times 0. Oh my gosh, that worked, and I get 0. If that happens, if you plug in an x value and you get a number, you're done. That's it. And I properly used equal signs here because I have a limit expression on the left and I have numbers on the right, and those two things can be equal to each other. Sweet. Down on this next one, if I try plugging in 2 squared minus 3 times 2 plus 2 is 0. 2 squared minus 4 is 0. Uh-oh, 0 over 0. So I can't just plug in and get an answer. The next step of my strategy is going to be to try some kind of algebraic simplification, and that usually means factoring. Now, I'm just going to point out again, I'm making a big deal about this, but especially if you are in AP Calculus, I mean, it's always good to use good math notation. It's always good to communicate properly. But if you're in AP Calculus and you write this on your page, your teacher should give you a 0 and not read any further because you just wrote this is called a linkage error. Okay, we just linked 2 things that weren't actually equal. We had a limit expression on the left, which is going to equal a number or something like does not exist, and we had a variable expression on the right, and those 2 things aren't equal to each other unless we're trying to set up an equation to solve, and that's not what we're doing. We're trying to compute an answer. All right, so I factored, no surprise, I can cancel out some terms. That usually happens. If you get 0 over 0 and you can't cancel out terms when you factored, double check your factoring. And now let's see if I can plug in. Indeed, I can. 2 minus 1 over 2 plus 2, 1/4. Da, 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 da. Last one here, limit as x goes to 0. As we said before, I have a 0 on the top, a 0 on the bottom, no algebraic way to simplify. The next thing I would do, if possible, would be to graph it. And here I've graphed y equals sine x over x. And we can see if I would zoom in on this, I can't, it's not a dynamic, I just have a picture of this graph. But if I zoomed in there, I'd notice that there's a hole. Because I cannot plug in x equals 0 for my function f of x equals sine x over x, I get 0 over 0. You can never divide by 0. That's always going to be some kind of discontinuity. So there's a hole there, but I can see just from the approach here as my x values get close to 0, if I project those arrows up onto my curve, the y values are getting close to this number, which is 1. And that allows me to say confidently that the limit as x goes to 0 of sine x over x is 1. That is using graphical or numerical approximation, using a graph table of values to approximate. Another way I could have done that, if I didn't have access to a graph, I could have typed in sine of 0.01 over 0.01 into my calculator, and maybe sine of 0.001 over 0.001. We'd also want to do some negatives, sine of negative 0.01 over negative 0.01, and see what kind of values you get. And I don't have a calculator on me, so I don't know exactly how many decimals we'll get, but it's probably going to be like 0.99, 0.99, maybe 0.9999. And that's, again, that's enough for me to say this limit equals 1. And notice the vocabulary I'm using there. The limit equals 1. The limit doesn't approach 1. The limit actually equals 1. The limit by itself, using that vocabulary, is a way of me saying approaching. This would be another graphical estimation, or using graphs and visual estimation to come up with our answers, but we have a couple of things to address here. So let's just jump down here to this very last one. This is an interesting one. Limit as x goes to 4 of f of x. So I'm letting x get close to 4, and think about projecting those arrows onto your curve. And I can see that those arrows are pointing right to, on the y coordinates, number 2, and that limit equals 2. But what if I asked you, let's go to, we're going to skip the first one. That's way too easy. What if I asked you this one? The limit as x goes to negative 4. So I make my arrows go to negative 4, and this guy on the right, those y values are definitely pointing to negative 2. This arrow on the left, those y values are definitely pointing to 3. Now, some people might think that the filled in circle here up at the y value of 3 means that that one's going to win, and that will be my answer, but I don't care, because remember, when we're looking at limits, we don't actually look at that number. We don't care what's exactly happening at negative 4. I want to know what's happening near negative 4. And the only proper answer I can say here is that this limit does not exist, because I got a different answer on the right as I did on the left. And whatever we know about the existence of things in math is that you can't have two answers. If I try to answer something this or this, that's probably not right. So the way we get around this, not really get around it, but the vocabulary we introduce, the notation we introduce in order to give us some kind of way to talk about these limits that are different from the left and from the right, is this little thing here. Notice how this question number 2 on this page says limit as x goes to 2, but it's got a little minus sign in the superscript. What that means is that I'm going to get close to 2, but only from the left direction, moving to the right, moving to x equals 2 from the right, or from the left, going rightward, basically from a negative direction. And in that case, that branch only goes to negative 1. And likewise, this guy, it's not a surprise to you then that if I come from the right, I'm going to do the same thing up here, and this one equals 5. All right, we got a couple more examples here I want to go through, and then I think we'll call it a day. We won't do all of them on this page. Some of them are just straight up factoring. This guy up here at the top, though, he's a fun one. Square root of 1 minus 1 is 0, and 1 minus 1 is 0. I highly recommend that you write out your work as you check that way, by the way, that you just write above and below. I'm not gonna say this equals 0. That would be wrong, because root x minus 1 does not always equal 0. So I'm just noting, I'm showing the person who's reading my work that I have evaluated the numerator and I have evaluated the denominator. Now I've got to factor this or do some kind of something. I can use graphical and numerical estimation. I don't want to jump to that until I absolutely have to. I'm going to suggest that we change our fundamental variable, just for funsies. What happens if I say, I'm going to consider square root x to be my fundamental variable that I'm dealing with, not x. So I'm even going to change this up here. If x is going to 1, square root of x is also going to 1. So limit as u goes to 1. Now root x would be u. x would be u squared. And lo and behold, this gives me an opportunity to factor in a way that I might not have considered before. Plus 1. Cancel those guys. Limit as u goes to 1 of 1 over u plus 1. 1 over 1 plus 1 is 1/2. Bum, ba, dum, bum. You might have seen a slightly more efficient way to do that. If you can just factor that denominator as root x minus 1 and root x plus 1, Godspeed to you, that's fantastic. You can save yourself actually like deliberately pointing out what your new variable is. You're doing the exact same thing. You're just kind of excluding the step of having to deliberately identify how you're changing what you're seeing as your fundamental variable. They're like variable of smallest unit, if you will. Let's do one more. No. Find a good one here. Here we go. Let's do this guy. Because there's one very last thing here I want to see. If I asked you the limit as x goes to 3 of f of x, that should be a very easy problem. As x gets close to 3, the y values get close to 1. No issue. Even if I ask you the limit as x goes to 4, this sort of situation is like exactly why we have the vocabulary of limits. Those y values get close to 2. Excellent. Hopefully you know what to do if I asked you the limit as x goes to 2. Let's go from the right, from the left, and then a double-sided limit. These would be all limits of f of x, f of x, f of x. From the right is 3. Sometimes this plus and minus can get really confusing because you're moving to the left even though it says plus, but it's like how you say the westerly winds are like coming from the west, right? So even though it's like moving left, the plus means coming from the right. This one coming from the left, that limit is going to be 2. And because those don't agree, hopefully this is easy, that I can say does not exist, DNE. The double-sided limit as x goes to 2 simply does not exist. Last interesting point on this picture, though, would be this one. The limit as x goes to 1. Take a minute and see if you can guess in your brain. What is the limit as x goes to 1? Hopefully you said 1. As x is getting close to 1, the y values are getting close to 1. But Mrs. Thomas, there's a dot right here. Oh, I'm aware. But when we're talking about the limit as x goes to 1, we really don't care about what's actually happening at 1. I'm going to ignore that entirely because I'm not asking about f of 1. That's what that would be. F of 1 is 2. That is an accurate statement. But as I get close to 1 from the right and close to 1 from the left, ignoring what's happening exactly right there, the y values that are approached are 1 and not 2. All right, I think that's it for this video. Hopefully you found this helpful. Just like and subscribe and keep watching, guys.